Hello, before we go on to the next sample problem, I'd like to make some correction in the previous video. So, dun sa previous video kasi, nabaliktad ko yung D1 tsaka D2. So, I interchanged D1 and D2. Okay? So, previously, D2 is here, D1 is here. And that should be incorrect, right? So, I corrected that. So this should be D1, this should be D2, so that we should interchange 3.1 and 2.7. Okay, previously, nandito yung 3.1, nandun yung 2.7. Anyway, I corrected that already here, and U2 should be 1.58 meters per second. And plugging that to the kinetic energy term, okay, it will result to a value of 0.531 newtons per kilogram. The previous value was, I think, something negative, right? Okay. Going back to the working equation, which is the Bernoulli equation, plugging in the values that we have completed so far. All right, we ended up, okay, that the value of the delta Z, or the height between the aorta and the left ventricle, okay, is 3.65 centimeters, which makes sense, right? Because in the literature, the average value is around an inch, right, or 2.54 centimeters. Okay, sometimes double that. Okay, the previous answer was, I think, around 12 centimeters, which is almost the size of the heart already. Anyway, let me discuss our last sample problem for the Bernoulli equation. Okay, we have here a cylindrical tank of diameter 1 meter, which has a well-rounded orifice of diameter 2 centimeters. So this is the tank diameter, right? And then there's like a small orifice here with a size of 0.02 meters in diameter. So the question here is, how long will it take an initial depth of acetone equal to 2 meters in height? Okay, so initially we have a 2 meter height of your liquid. How long will it take that to drain the tank completely? Okay, so we're given here the specific gravity of acetone to be 0.79. We'll not use this value, however, because in the mechanical energy balance equation, we will cancel the pressure term. Okay, the reason is that I wasn't able to mention this problem, but this tank here, okay, the opening is open to the atmosphere, and of course, since you have like a puncture here, kaya nga nagde-drain yung liquid, okay? So butas din yan, and we will assume that it's also open to atmospheric pressure, okay? So therefore, the difference between the pressures at these 2 points here will be 0, okay? And since the pressure term includes the density as the denominator, okay, hindi na natin gagamitin yung density or specific gravity ni acid. Anyway, I will present to you two solutions for this problem, and only one would be quite correct. Okay, so what I mean is that there are two approaches to solve this problem, pero isa lang doon yung pinaka-accurate, yung tama. Okay. The first approach is to assume that we have a steady state condition, and thus, if we have a steady state condition, we will be able to apply the Bernoulli's equation. Okay. Again, so here's our sketch. So this is 0.02 meters because that's 2 centimeters, and then diameter is 1 meter. The initial depth of the acetone is 2 meters. Okay, let's take this as 0.2, and then 0.1 yung initial height. Okay, so what we're going to calculate is the time to drain the tank. Okay, so here is the mechanical energy balance equation. Okay. And we would like to omit some terms from that. Okay, if we're going to assume, again, I've already mentioned a while ago that we will use Bernoulli equation, but I'd like to start everything from the mechanical energy balance equation. Anyway, if we're going to assume that the fluid is inviscid, there are no frictional dissipation, then we will omit this frictional term here. Okay, and in this sketch, in the problem, there's no mention of any work like that from a pump or whatever. Okay, so we can eliminate the work term. So we ended up with this, but there's some term that we can still omit. Okay, I mentioned a while ago that the difference in pressure between these 2 points is 0 because both are open to the atmosphere as we assume. So therefore we can cancel this term. Okay, so ang natira doon sa equation ay delta U squared over 2gc plus delta Z GGC equals 0. Okay, now if we're going to look at this, the diameter, okay, of the tank is greater, it's a lot greater than the diameter of the orifice. Therefore, we can say na yung velocity ng fluid, okay, at this point, 0.1, or at this point rather, 0.2, kasi ang liit ng butas dito, mabilis compared sa velocity at 0.1. So U2 is much greater than U1, a lot greater than U1. Okay? Therefore, we can probably, in this kinetic energy term here, sobrang baba ng U1, so we can assume that it's negligible. Okay, let me use another thing there. Okay, so 0. Okay. Now let's say that the difference between 0.2 and 0.1 in height, right, is negative h. Okay, kasi this is 0 kasi nandiyan yung datum line natin, nandiyan yung initial point. Sa baba niya, negative 2. Okay, so let's first use, instead of negative 2, let's just say negative h so that we can just plug in the values later. Okay, so that will become, na-cancel natin to, U2 squared na lang ang natitira over 2gc. Plus delta Z GGC, delta Z, which is Z2 minus Z1, we named that already to be negative h equals 0. Okay? Now, rearranging this further, okay, ganyan, and ganyan, right? We just rearrange the equation. We can cancel GC here, okay, and then we still have the square of U2 sa left-hand side ng equation. So what we need to do is to take the square of both sides. So therefore, U2 is equal to square root of 2gh. And this is a useful formula, which we call as Torricelli's theorem. Okay, so basically what that means is that if you have a puncture here, okay, if you want to get the velocity at that point, okay, it's the same as the free fall velocity of your fluid along this column, right? So it's square root of 2gh. So let's use that. U2 is square root of 2gh, right? So again, U2 is the velocity right here. But again, let's go back to the question. Whereafter the time to drain the tank? And where do we refer or base our solution to? Sa anong velocity? Is it the velocity right here or the velocity at that point? Okay, so dyan pumapasok yung tinatawag na natin steady state assumption. So if we are going to assume steady state, okay, and obviously, ang gagamitin nating velocity to be used to calculate the time to drain the tank is yung velocity dito. Kasi the fluid spends most of its time dito sa along this 2 2-meter length. Tama? Okay. Why? Because in the whole thing, this velocity, U1, okay, is sort of the rate limiting step of the process. Therefore, it will dictate the overall speed to drain the tank. All right? Okay, so we will use, therefore, U1. Okay. How do we get U1 from U2? Well, we can use the continuity equation. So the volumetric flow rate entrance is equal to the volumetric flow rate exit. U1A1 equals U2A2, where after U1, we know U2 as square root of 2GH, and we can know A1 and A2. Okay? So doing that, U1 equals U2, A2 over A1. A is simply pi over 4D squared. So for both the numerator and the denominator, so we can cancel pi over 4. Ang natira is U1 equals U2 D2 over D1 squared. Substituting U2 here, so U2 is square root of 2GH. Okay. And then for D2 over D1, okay, yan pa rin siya. Substituting the values, square root of 2, G is 9.8, H is 2 meters, okay. D2 is 0.02, that's the size of the puncture or the orifice. D1 is the size of the squared. So you will get 2.5 times 10 raised to -3. This should be -3 meters per second. Okay. Now to get the time to drain the tank, okay, what we have to do is to just divide, okay, yung distance over the velocity. So that's the time. So 2 meters divided by 2.5 times 10 raised to -3. This -3. And therefore, you will compute that to be 798.2 seconds or 13.3 minutes. Okay, so that's one approach to solve the problem. But in some cases, you cannot really assume the system to be at steady state. The reason is that even though U1 here is very slow, it still has a value. Okay, so the second approach, which is the more correct one, okay, is to use the what we call the quasi-steady state assumption. Okay, so it's sort of an unsteady state solution, but it really is a quasi-steady state solution. So we will pick up from this part where we got already the expression for U2, square root of 2GH. So hindi mababago yan, okay? But we're after again U1, right? So how do we compute U1? Previously, dun sa steady state assumption natin, U1 is yun yung hanapin natin, right? And then we will be able to calculate that time to drain the tank, okay? And we use the continuity equation. But in this new approach that we'll do, ang mangyayari is that we will assume U1, okay? We will know that U1 is actually related to what? The change in height per time, okay? The derivative of h per t, negative, no? So from here, we can plug in these two expressions to the continuity equation. So U1 is again the negative dh dt, and U2 is square root of 2gh. We have A1 and A2 here in the continuity equation. Just plug in that, canceling pi over 4. So we ended with D1 squared and D2 squared. Now we will rearrange the expression, okay? So that we can actually, what we're going to do is to separate the variables, okay? So because what we obtain here is actually a variable separable differential equation. So here, pinagsama ko na yung dh tsaka si square root of h. Negative nilagay ko dito, right? And this whole thing, square root of 2g d2 over d1 squared, it's basically constant na to lahat. So ang natitira na lang dito is dt. So if we're going to integrate, okay, with certain limits, okay, so this will integrate from 0, yung initial surface nung liquid, di ba? Okay, to negative h. Okay, kasi di ba ang problem ng negative 2, right? Of course, later on we'll be able to know that the limit here is really negative 2. Gagawan, ang nilalagyan lang muna natin yung letter, right? Yung variable para diretso substitute na. So while here it's from 0 to a time t. Okay, so actually nandito na siya. And performing the integration, so you will get the integral of this part is 2 times square root of negative h. And ito, integral of dt lang naman to, so it's time. So solving for time, you will use this expression there for rearranging, right? So plugging in the values, we know negative h is negative 2, right? So negative of negative 2. d1 over d2 is 1 over 0.02, and g is 9.8. Solving that, we obtain a value of 1596 seconds or 26.6 minutes, which is double than the previous answer, 13.3 minutes. Okay, so this should be the more correct approach.